We just saw how to grow a classification tree using the CART methodology, and in this video we'll take a look at some generalizations of this type of procedure. So the first type of generalization regards the error measure that we used. Remember, we had this E sub r, which was where is that? So E sub r was the fraction of points in this region R, that was a subset of d-dimensional real space, the fraction that would be misclassified if we use a majority vote in that region. And we used this sort of metric, this E sub r, as our criteria for splitting. And this is what is referred to, well, in this context at least, they refer to as an impurity measure. So let me say different impurity measures or quantities. So the first one was this E sub r, and that's the misclassification rate in the region R. Another one which can be used is the entropy H sub r, and this has a very nice interpretation actually. If we have this, we'll redraw this little picture for our reference. We had some points. Oops, let me make that blue. So we got some blue points here, and we've got some red points. And if for some region R, maybe this is our region R, if we look at the empirical probability distribution on this region, that was this thing that we were talking about earlier. We had this fraction of points. This is defines an empirical probability distribution over the classes in this region. So in this case, this empirical distribution has, let's call the blues 0s and the reds 1. So the probability of 0 in R, maybe we should denote by subscript R, something like that, is, so we said blue 0, so that's 3 out of 4. And the probability of 1s is 1/4. And if we had other classes, we could have probability of 2, and so on. So another option here, instead of using the misclassification rate, we could use the entropy. The entropy of this distribution, which is the sum over classes. So maybe I'll write C. Well, we were using Y before for classes. Let's stick with that. So the sum, let me just say, I'll just say Y over all. This is some finite set of classes. And I should mention, these are all generalizations for the case of classification. So the possible classes are some finite set, and we would sum over these. And we have this empirical distribution times the log, and it's minus this quantity. That makes the entropy positive. So instead of using the misclassification rate, you could instead use the entropy, and this has actually a very appealing interpretation, which is we want to choose a split. Let's go back to one of these earlier examples here. So in our very first example, when we were talking about decision trees, we had these 1s, reds, and the blue 0s, and we said, well, let's make our first split here. And this was appealing because that made this whole region all have the same class. And therefore the empirical distribution would be, the probability of 1 would be 1, probability of 0 would be 0, and so the entropy would be 0 for this region. So right, if we computed the entropy, wherever it is. So the probability, by convention, we take 0 log 0 to be 0. And 1 times log of 1 is also 0, because log of 1 is 0. So the entropy for that left-hand region, go way back up to our example here, is 0. And we would get some entropy over here, which is not great, but you can think intuitively, at least, that this, using the entropy, you're trying to be as certain as possible about what's going on in each of the regions that you're splitting it into. So you want to make each of the regions as homogeneous as possible. That's what the entropy is doing. If you used the entropy instead of the misclassification rate, and if you use this, you would just plug it directly in back here, wherever it is in these criteria. You would just use the entropy of the region instead of the misclassification rate. Another generalization, another option people use, which I won't go into too much detail, I'll rate it as G sub R. It's called the Gini index. Sometimes people use it, often used for this type of impurity measure in this setting of CART. And the Gini index is the sum, again, over y's, just like here. And this time it's probability of y times 1 minus the probability of y. So that's all the Gini index is doing. And so these are some ways to generalize that previous. These actually are recommended. The entropy and the Gini index tend to work better than the misclassification rate, so probably is better to use one of those. And also the Gini index has some nice analytic properties that make it work better make it easier to work with. Let me mention, now I'm going to follow the book. I'm going to mention a few other issues associated with this CART model, and I'm going to follow so Hasty, Tibshirani, and Friedman have a book called, what's it called? The Elements of Statistical Learning, and I believe it's available freely online. And I'm just going to mention a few other issues that they talk about. Well, I'll follow the order that they talk about them here. So categorical predictors, in the sense that the predictors, the features xij, each of the different j's, may not be a real number. So you might have one of your features might be just from some finite set, some arbitrary set of possibilities. And so you can't do that trick. It doesn't make sense to talk about, well, I mean, I numbered them here, but if they weren't ordered, it wouldn't make sense to talk about splitting when this is like less or equal to some value. That's not really meaningful in the setting where you just have some abstract set. But it turns out there's a very clever trick that one can use, at least in the case of binary classification, to very efficiently find the optimal split, even for categorical predictors. So that's a very nice thing. Another possibility, something that might come up, is if you have a loss matrix. In other words, it's not, predicting one class when you should have predicted another. It's not necessarily, the error is not necessarily the same for different types of errors. And this can also be incorporated into the growing the tree procedure. You can incorporate the loss matrix in a smart way. Another issue that might come up is if you have missing values. So we were assuming that we had these, right? We had these x1, y1s, etc. And it might turn out that some of the values, like maybe x1j for some j, is missing. It's just not available. It's NA. And it's just blank. So it turns out that there's, well, one way that this can be handled, the recommended way, is to use what's called surrogate variables. I won't go into that, but I just want to mention so you're aware. Another thing which you might be sort of wondering about is we only were considering binary, not only binary splits, but also we were only considering splits that were sort of aligned with one of the axes, which seems like a very rigid, very restricted type of split. I mean, why not allow splitting along something like this, linear combinations at least? And there are models where you can do this. There are generalizations in which you can split on linear combinations instead of just along one coordinate. But in fact, it turns out that for whatever reason, these one thing is that it's less efficient. It's much less efficient. There's not a very efficient way because there's many more possible linear splits. Well, there's infinitely many. And another reason why you might not want to do this is because it doesn't, at least empirically, people have found that it doesn't tend to give much better performance, which is kind of surprising. But that's especially when you combine this, the cart model with the aggregation techniques that we're going to talk about very briefly. And so the one last thing which will lead to these aggregation techniques is there's this instability in these trees, in the sense that a very small change in your data set could result in a very drastic change in the resulting tree. So it's very sensitive to the data, and this instability makes the resulting tree have what we refer to as high variance. The estimator in statistical speak has high variance, and so as a result, it generally has lower performance. But there's a fantastic way to get around this, or at least to mitigate it to some degree, using aggregation, and that's what we're going to talk about next.